Hey everyone, welcome to the Explainer. Today we're jumping into a real classic interview problem, merge sorted array. Now on the surface, it sounds pretty straightforward, right? But to solve it efficiently, you've got to flip your thinking on its head. The best solution here is probably not the first one that's going to pop into your mind. Okay, so let's get right to it. Imagine this. You've got two sorted lists. Your job is to merge them into one big sorted list. Simple enough. But here's the catch. You can't use any extra space. No new arrays allowed. The final merged list has to be built right inside the first one. So, take a second. How would you even begin to tackle that?
So, formally, this is what you'll see on LeetCode. Problem number 88. We get two sorted integer arrays, nums1 and nums2. And the goal is to merge nums2 into nums1. Now, here's a super important detail. You're also given m and n. These aren't the total lengths of the arrays. No, m is the number of actual numbers in nums1, and n is the number of numbers in nums2. The problem guarantees that nums1 is big enough, it has a bunch of empty slots at the end, just enough to fit everything from nums2. And the big rule, of course, is we have to do this in place.
Let's make this super concrete with an example. Look at nums1 here. We've got 1, 2, 3, and then 3 empty slots, which are represented as zeros. So m, our count of real elements, is 3. Then you have nums2 with 2, 5, 6, so n is also 3. What we want to do is end up with nums1 looking like this final output, 1, 2, 2, 3, 5, 6. All sorted, all inside that original array.
All right, so when you first see a problem like this, what's the gut reaction? For most of us, it's probably the most straightforward, maybe even the lazy way. Let's just make our lives easier and use some extra memory. And this method is pretty easy to think through, right? You just, create a brand new temporary array, then you'd set up a couple of pointers, one for nums1 and one for nums2. You'd walk through both, picking the smaller element each time and popping it into your new array. Once you're done, you just copy the whole sorted temp array back into nums1. And look, it gets the job done. It works. But there's a pretty big catch, and that catch, that hidden cost, is all about space. This approach has what we call a space complexity of O of m plus n. In plain English, that just means the extra memory you need grows right along with the size of your input arrays. And if you're in a coding interview, that's often a no-go. The interviewer is almost always pushing you for an O of 1 space solution. That means solving it using no extra memory. That's the real puzzle here. So, to get to that slick O of 1 solution, we've got to go back and look at our inputs really carefully. Let's ask a simple question. Where is the empty, usable space in nums1, right? It's not scattered around, it's not at the start, it's all packed neatly at the very end. And that observation shows exactly why our first idea was kind of clunky. We were trying to build our new sorted list starting from the front, but that's where all our important numbers are. Every time we'd place an element, we'd be in danger of overwriting another number that we haven't even looked at yet. It's a mess. So, if all the free real estate is at the end of the array, why on earth are we trying to start our work at the beginning? And that question right there, that leads us straight to the aha moment. The key insight, the whole trick to this problem is beautifully simple. Work backwards. Instead of starting from the front and causing chaos, let's start filling the array from the end where all that lovely empty space is just sitting there, waiting for us. This idea of working backwards brings us to the optimal solution. We're going to do a 2-pointer walkthrough, but this time we're filling the array from the end. Let's see how it works. Okay, here's the setup. It all comes down to 3 pointers. First, we have a pointer, let's call it I, that points to the last real number in nums1. That's at index m-1. Next, we have pointer j, pointing to the very last number in nums2, at index n-1. And finally, we have our most important pointer, k. Think of k as our right pointer. It starts at the absolute end of the nums1 array, at index m plus n-1.
And here's what that looks like with our example. You can see pointer I is sitting on the 3 in nums1. Pointer j is on the 6 over in nums2, and our right pointer k is all the way at the end of nums1, just waiting to place the largest element of the entire merged array. Okay, so the algorithm is basically a little dance that happens in a loop. At every step, we just do one thing. We compare the number at pointer I with the number at pointer j.
Whichever one's bigger has to be the largest overall number we haven't placed yet. So we take that bigger number and drop it into the spot where K is pointing. Then we just move the pointers. We move whichever pointer we just used, I or J, one step to the left. And we also move our right pointer, K, one step to the left, ready for the next biggest number.
Let's walk through the very first comparison. We're looking at nums1's I, which is 3, and nums2's J, which is 6. Well, 6 is bigger, so we copy that 6 into the spot K is pointing to at the end of nums1. And just like we said, we then move J to the left, so it now points at the 5, and we move K one step to the left to the next empty slot. See? No overwriting. It's clean. And from here, we just rinse and repeat. Next up, we'd compare the 3 at I and the 5 at J. 5 is bigger, so it goes into the K spot. Then we move J and K again. Now we're comparing 3 and 2. This time, 3 is bigger, so it gets placed, and now pointer I gets to move. You see the pattern? We just continue this little dance, filling nums1 from right to left, always putting the largest remaining number in its correct final spot.
Okay, that's the logic down. Now let's see what this looks like when we actually turn it into code. Let's code up this in-place solution. The absolute core of our solution is this one while loop. It's set to run as long as we have numbers left to compare in both arrays. So as long as I hasn't gone past the beginning of nums1 and J hasn't gone past the beginning of nums2. And inside this loop, well, that's just the compare and place logic we've been walking through.
But wait a minute, that while loop stops as soon as one of our pointers, I or J, runs out of road. So, what happens if we use up all the numbers in nums1 first? What if pointer I drops below 0, but there are still a few numbers left over in nums2? That's a really important edge case. And the solution is so elegant. It's just this one extra tiny while loop. You can think of it as our cleanup crew. All it says is, hey, if there are still any numbers left in nums2, just copy them over to the front of nums1. So why is that safe? Why can't we just copy them blindly? Well, think about it. If our main loop finished because I ran out of numbers, it means every single remaining number in nums2 must be smaller than anything we ever looked at in nums1, because if one of them were bigger, we would have placed it already. Since everything's sorted, those leftovers in nums2 are guaranteed to be the smallest remaining numbers, so they just fill in the front of the array perfectly. And you might be wondering, what if nums1 has leftovers? We don't need a loop for that, because if nums1 has leftovers, they're already sitting exactly where they're supposed to be. And there you have it. We've totally cracked this problem. So let's wrap up with the key takeaways to really make this solution stick in your head. Okay, let's boil it all down. First, the pattern to recognize here is 2 pointers used for an in-place modification. The absolute game-changing insight: work backwards. Start from the end where the empty space is and you avoid all the headaches. This brilliant move gets us to a time complexity of O of m plus n because we touch every element just once. And, most importantly, a space complexity of O of 1. That's the gold standard, no extra memory required. So this whole work backwards thing, it's not just a one-trick pony. It's a seriously powerful technique for your toolkit. So the question I want to leave you with is this. What other array problems have you seen? Problems that seem really complicated or messy when you try to solve them from left to right, that might just become simple if you try tackling them from the end.